Jordan Mirocha, Galaxy Formation from the Moon, a Forecast.
All right, thank you. I'll wait for my slides to show up here. Don't look. All right. Thanks for being here. I'm Jordan. I'm at UCLA now. I'm going to be talking about a lot of work that I've been doing with Steve Frolinetto at UCLA, who leads the DARE theory group. And much of the work I'll describe was in collaboration with a former student of his, Jason Sun, and Jack Burns, who's at Colorado, who's our fearless leader of DARE. So what you're seeing in this panel here are several models for this global 21 centimeter signal to be targeted by edges on DARE, as you heard from Raul. And so my goal today is to just sort of provide some more science context. What is the science case? Where do our predictions come from, and why is that driving us to low frequencies? So it's actually not a problem that you saw my last slide first, because I'm going to show it first anyways. Okay, so if you don't remember anything in this talk at all but one thing, you should just remember, well, two things, each of these figures. Okay, so what I'm showing you here is something called the galaxy luminosity function, some recent data from the Hubble Space Telescope. And this is a measurement of how many galaxies there are as a function of their brightness. Okay, so bright galaxies are over here, they're very rare. Faint galaxies are very numerous, they're up here. And you can tell there's this big gap in the data where we don't see a lot of faint galaxies. Okay, that makes sense. And you can tell there's this sort of bifurcation at the faint end, where depending on how you extrapolate, you can get very different answers, which doesn't look like much. Okay, but if you look at the global 21 centimeter spectra that correspond to those luminosity functions, you can see quite a bit of variance. Okay, at sort of measurable levels. Okay, so what I'm going to show you today in my talk is that recent luminosity function measurements by Hubble and in the next few years with the James Webb Space Telescope really provide an important anchor for our 21 centimeter based predictions. Even though these observable signatures are extremely different, the underlying science of interest is the same. Okay, and so what we're going to find is that when we kind of tie our models to these independent data sets, we come up with predictions that really tell us that the lunar far side is the ideal place to do these experiments. And it's because we're seeing a preference for sort of low frequency features of interest. Okay. Okay, so now my outline, now that I've told you the punchline, I'm going to give you kind of a crash course in first galaxy science in the global 21 centimeter signal. I'll describe our results in the context of Hubble and James Webb, and then I'll close with sort of the observational consequences of these new predictions. Okay, so this is the big picture. Okay, so Raul showed you this diagram from top to bottom. I'm going to show you it from left to right. Okay, so the cosmic microwave background now is all the way on the left. That's something like 400,000 years after the Big Bang. And the time scale here from left to right is kind of logarithmic. So the first giga-year is really, 2/3 of this, with present day all the way on the right-hand side. And so really what we know are the boundary conditions of this problem. Okay, we know in a lot of detail now about the cosmic microwave background, fluctuations in the initial matter-power spectrum, and so on. And we sort of know that this transition called reionization ended at redshift of 6. But we know very little about what's happening in between. So these are sort of the formative years of galaxy evolution when galaxies are first starting to form and setting the stage for what galaxies look like thereafter, starting kind of after reionization. So the big questions here, as Raul pointed out, just simply when did the first stars and black holes form? Sort of more interestingly, what were their properties? Okay, there have been theoretical predictions in the literature now for about 20 years that suggest that the formation channels of the first stars and black holes should be entirely different from the formation channels of stars and black holes today. So we want to try to test those predictions observationally. And then, we know when reionization ended. We have some ideas about what sources were responsible, but we don't really know how it began. And so this is intimately linked with the properties of the first stars and black holes. Okay, so our approach here is really complementary to the Hubble Space Telescope and James Webb Space Telescope, which are looking for individual galaxies. But those galaxies lie at great distances. Many of them are extremely faint. And so while they are individually very faint, in aggregate, they have an enormous impact on the intergalactic medium, okay, the IGN. And so the whole point of 21 centimeter astrophysics and cosmology is to leverage the fact that individual galaxies are faint, but their sheer numbers drive really interesting evolution in the properties of the IGN. So if we can understand how to reverse engineer this problem, measure the IgM, we might infer something about the first galaxies. Okay, so the basic physics goes as follows. We have the cosmic microwave background, which is behind everything. Okay, so it's our backlight, clouds of intervening hydrogen gas, and then our observatories on the ground or in space. And we're really looking for a spectral distortion against the cosmic microwave background. Okay, so you can imagine as CMB photons travel through space, they may or may not encounter clouds of neutral hydrogen gas. And depending on how the ground state hyperfine levels of these atoms are populated, you'll see this in either absorption or emission. Okay, and if a cloud is ionized, you won't see anything at all. Okay, the CMB photons will pass straight through. Okay, and so our observable signature is this differential brightness temperature, which you can see goes as the neutral fraction of hydrogen. Okay, so if the neutral fraction is 1, it's sort of maximally strong, but if the gas is ionized, we see nothing at all. We're doing sky average experiments, so we ignore the density evolution. And then this really important quantity called the spin temperature. Okay, so the spin temperature is really just a way of quantifying the level populations of hydrogen atoms on average, and that you can see governs the sign of this signal. Okay, so if TS is very small, we get a negative or absorption signal. If TS is very large, this whole expression actually saturates, and there's sort of a maximum allowed strength of the signal. Okay, so what we expect qualitatively is a signal that can kind of wiggle around depending on how you think the first stars and black holes work. Okay, so this is sort of a toy model where we have a bunch of scaling factors, and you kind of know you're in trouble when your parameters are F subscript, okay, but because that's how we parameterize our ignorance typically. Okay, so these are factors that relate to the production efficiency of Lyman alpha photons, X-rays, Lyman continuum or ionizing photons, and then just the overall efficiency of star formation. Okay, and so if I play that again, you can see that just varying these each independently by a factor of 10, or maybe I did 100, moves the features of this signal around pretty considerably. Okay, and I'm looking at sort of low frequencies here, 170 megahertz and below. Okay, but the point I want to get across in this talk is that we don't know nothing, all right? So the last plot was just twisting knobs and seeing what the signal could possibly look like. But as I've told you, Hubble and soon the James Webb Space Telescope are starting to build up a picture of what galaxies are doing in the early universe. Okay, and so I'm going to describe how we think of this from a theorist's perspective and try to tie in the observations in a second. But so if we kind of start from first principles, we know that, or we think that galaxies live in dark matter halos in the universe. And you can describe the abundance of dark matter halos with something called the dark matter halo mass function, which is what I'm showing here in a cartoon sense. And it's just the number of halos per unit volume in the universe as a function of their mass, okay? So as is usually the case, you have lots of little things and not very many big things. Okay, so what's really interesting is if you try to then plot the galaxy luminosity function on these same axes, the shapes are different, okay? So we think that dark matter halos are occupied by galaxies in roughly a 1-to-1 fashion. And so then we got to thinking about, why these shapes are different, okay? So if every halo gets a galaxy, then what this is telling you is that at low halo masses, galaxies are less luminous than they kind of should be. And at high halo masses, galaxies are less luminous than they kind of should be. But somewhere in the middle, there's a sweet spot where galaxies are sort of maximally luminous for their halo mass. And so in trying to make sense of this, what you can say is, well, I think the luminosity of galaxies is proportional to star formation rate in galaxies, which makes sense. These searches with Hubble target the rest frame ultraviolet emission of galaxies. And you might say, well, then the star formation rate in individual galaxies is proportional to some star formation efficiency, which is going to encode really the physics of how star formation works, and just the rate at which the halos themselves are growing. Okay. So it turns out you can predict from theory what this is incredibly accurately, or you can simulate it on a big supercomputer. And there's kind of a growing consensus of what this function is, which means that the difference of these curves you can use to get an estimate of this star formation efficiency, okay, as a function of halo mass and potentially redshift or time. Okay, so if you do that, you get a curve that peaks somewhere in the vicinity of 10 to the 11 solar mass dark matter halos, and on either side it's dropping pretty rapidly. Okay, so small galaxies are forming stars less efficiently than galaxies of this mass, and galaxies a little bit more massive than that rapidly start becoming less efficient at forming stars. Okay, so I should point out that basically understanding why this has this shape, this function has this shape, I don't think it would be an overstatement to say this is what most people in galaxy evolution are working on. Okay. How is it that low mass galaxies are so much less efficient at producing stars than high mass galaxies? And then how are fortunes reversed so quickly at this sort of critical mass? Okay. So I'm not going to dwell on sort of the interesting questions underlying this curve, but I'm going to say let's use this curve to make some predictions. Okay. So the first thing I can do with that curve is I can plot the luminosity function. Okay, I've just described the relationship between mass and light. And then, so by construction, it fits the data. And so this is my kind of second slide all over again. And depending on what happens at the faint end, which we don't know now, you get global 21 centimeter spectra that vary by 10, 20, 30 megahertz in their position, but are relatively strong in the millikelvin sense. Okay, so we also have some independent constraints from the cosmic microwave background. I can count up all the photons produced by galaxies according to this curve at all times, and get a constraint on the integrated column density of electrons from my eyeball to the cosmic microwave background. So our models sort of satisfy that constraint. And recently there have been some 21 centimeter interferometers that also give us a constraint on the spin temperature in the redshift 8 intergalactic medium. Okay. So we're trying to put this all together and say, you know, not what happens if we twiddle these knobs, what are the kind of whole realm of possibilities, but what is our best guess? What's our vanilla model for what the signal should look like? So if we limit ourselves to just the kinds of galaxies that we think we know, you get curves like the dashed one. That's just sort of our vanilla model. If you then say, well, I just want to kind of ramp up the UV luminosity of galaxies as much as I can within reason, and the easiest way to do that is to just dial down their metallicity, which makes sense. In the early universe, there hasn't been a lot of time for stars to form. Okay, so you can make things happen a little bit earlier, but that's about as far as it goes. Okay, so we're at the point where we're expecting a signal that kind of no later than redshift 10, so frequencies no higher than about 120 megahertz. Okay, but we don't actually think this is the whole story, and this is where things get really interesting. Okay, like I alluded to in the beginning of my talk, we think that the formation channels of the first stars and black holes are very different. Long story short, it's because the gas out of which these objects are forming is primordial. Okay, there are no heavy elements. When you invoke these sorts of populations, you introduce new, predominantly, exclusively, low frequency features in this signal. Okay. So depending on the relative efficiency of their ultraviolet and X-ray photon production. Okay, so this is really the story of my talk, is that when we try to anchor our predictions to independent measurements, we come up with this picture that is pushing us to lower frequencies. And as Raul pointed out, we have these challenges in the vicinity of 100 megahertz due to RFI, and the ionosphere frequency is lower than that. And both of these things have led us in the DARE group to think about doing this from the moon. And from the moon, you still have other things to worry about, like our own galaxy. But we've shown through numerical experiments that even with a spectrally smooth but very strong galaxy, you can extract the parameters of your model fairly robustly. Okay, and so we've written a couple papers about this in the last year or so. So I think I'm about out of time, so I will throw up my summary slide and then take any questions if you have them. Thanks.
I have a question.
Sure.
At the high mass end of your halo, isn't one of the reasons you have trouble with star formation is feedback from AGN?
That's what a lot of people think at low redshifts. It's not clear that that should
well,
continue
sure.
at kind of arbitrarily high redshifts, but it does appear to be there, which is interesting. So something we're thinking about.
Okay.